Today's lecture is in seismic stratigraphy. We will be talking about the reflection continuity. And the continuity of the reflections actually depends on the continuity of density velocity contrast, which give us an indication of the continuity of bedding surfaces or unconformities. And we extract information about the positional process and environment. As you can see from the figure on the right side, lateral continuous reflections and discontinuous reflections with angle relationships. Also, it provides information about the positional process and environment, and as long as the reflectors are continuous, indicate uniformly stratified deposits. So reflection patterns showing reflection terminations indicate stratigraphic relationships. So once you don't have any continuity, you have discontinuities or terminations, and those we call them stratigraphic relationships, such as on lap, down lap, and top lap, as you will study that in basin. This figure shows different kinds of terminations. You can see the top lap on the top, on lap on the left side, truncations, down laps, and the difference between the sequence boundary here and the down lap surface and apparent truncation, and so on. Now we come to the amplitude. The amplitude is a seismic wave height, as all of us know, and is a function of energy of seismic waves. The amplitude also is measured as distance from the mid position of wave to the extreme. So what is the story of behind the amplitude with seismic stratigraphy? It relates to the impedance contrast between beds and provides information about the bed spacing. Bed spacing, sometimes we call it like a thickness, and to some extent fluid content too. So high amplitude and high lateral continuity indicates low energy quiet water deposition, while high amplitude and low lateral continuity indicates heterogeneous deposition, such as interbedded channel sands and shales. If we have low amplitude and high lateral continuity, this will indicate deep water. So the amplitude is controlled principally by the velocity and density contrast. This is the main point. It is affected also by spacing between the reflecting surfaces, where bed spacing is optimum. Optimum means you can see it using the seismic reflection method. Energy responses are phased together, like constructively, to intensify and amplify the reflected energy, and in this case we can see the top and bottom of this. For example, if the bed thickness is less than the wavelengths of the seismic wave, for example, like for example 1/4 of wavelength, the reflection from the top and base of the bed can be phased together to give a large. But if the bed is very thick, the reflection from the top and base of the bed are completely separate. So the amplitude is a function of acoustic impedance. Lateral changes of amplitudes will give us indication about changes in the character of bedding thickness. And the last thing here about those characters is the interval velocity, and it is direct indication of lithology. As we know, every specific lithology, it has its own velocity, but no unique seismic signature. You cannot just tell by this velocity this is sandstone or this is limestone, okay? And we have to study that in detail later. So the interval velocity, seismic velocity over depth of depth interval Z or Z, if the rock type is uniform through the depth, then this interval velocity equal to the formation velocity. If the depth interval covers a number of rocks, we have rock beds, we have different number of beds, then the interval is equal to the average velocity calculated over this the distance z or depth. So we have many many layers here, zi, which where I indicates the number of beds of interval, and ti is one-way travel time. Then the interval velocity equals zi over ti. Okay, so next lecture we will learn about seismic resolution as an important parameter also in using seismic reflection method in seismic stratigraphy. Thank you.